So I'm going to talk about some results that are kind of pushing how much we can get from this principle of non-contextuality that I'll explain. Basically, we show that in general, so that's kind of the first part of the talk, in general, they, especially once you take into account transformations, non-contextuality puts surprisingly strong constraints on your models. And then in the second part of the talk, I'll focus specifically on the stabilizer subtheory of quantum mechanics. And there we find that the constraints are actually so strong that there's only one non-contextual model in odd dimensions. So yeah, kind of overall the theme is that this single principle of non-contextuality can really tell you quite a lot about the form of your ontological model. And from a foundational point of view, I think the most exciting thing about this results is, well, we know we can't have a non-contextual model of all of quantum theory, but if we were to imagine somehow tweaking the definition of non-contextual model, relaxing one of the background assumptions somehow so that you could have a non-contextual model of quantum theory, then it would be possible that that model would be very constrained or even unique. So this kind of gives hope that non-contextuality allows you to derive the ontological picture from operational facts. Okay, so I should start by explaining what this non-contextuality is that I'm going to be talking about. Sorry, I should say it's joint work with all of these people, and I believe John Selby should still be there, so you can go bother him if you have questions that I don't give you a good answer to. Okay, so what is this this non-contextuality that I'm talking about? So it's based on a kind of principle that says you should, if you're going to talk about what's going on, you shouldn't posit that there are distinctions that don't make a difference. Or in Leibniz's language, it's about the identity of indiscernibles. So more specifically, we're supposing that we call what we normally talk about in quantum theory the operational level. These are the probabilities we see in an experiment. And we're supposing that there's some underlying ontological explanation of that. But we want that explanation at the ontological level doesn't have any distinctions that don't make an operational difference. So what is this ontology I'm talking about? Well, at the operational level, we might have some procedure for preparing, transforming, and then measuring a system. Can you see my cursor?
You can see your equation, so...
but can you see where I'm pointing with my cursor?
No.
Oh, that's nice.
Now we see your pointer, but not your slide.
It's one or the other.
Sorry. But we know now where to look.
I don't know how to. Oh, it's infuriating. I've told it I don't want to annotate anymore, and it's still insisting.
So now it's all black. Okay, can you share your screen again? Now we just see you, but not your slides.
That's what I'm trying to do. Okay, I'm not going to try annotating again. Okay.
Okay.
I guess I can do that. Okay, where were we? Yeah, okay, so at the operational level, you have this thing. You have some way of preparing, transforming, and measuring the system. And then you'll have some probability for the measurement outcomes you get from that final measurement. So this is just the thing you would predict in quantum theory using the Born rule that we were just hearing about. Okay, but then we notice that the way we prepare the system seems to change the probability for the measurement. And so we try and explain that correlation by imagining that there is actually a physical system going from the preparation to the measurement, that system has some kind of properties that we just encapsulate in this thing called the ontic state lambda, and that the measurement reveals those properties or aspects of those properties, which is what explains the correlation. Okay, but we don't assume that thing is necessarily deterministic. So when you prepare the system, you have some probabilities for which ontic state you're going to get. When you transform the system, you get some new ontic state, lambda primes, that can depend on the initial ontic state and your transformation. And then when you measure the system, the probabilities for the different outcomes depend on that new ontic state. And the important assumption here is that this probability for the measurement outcome only depends on the preparation of the transformation via the ontic state lambda. Okay, it's not allowed to just directly depend on the preparation or the transformation. So this lambda screens off the correlation. Okay, so that's just the basic ontological models framework. And if you just want this basic framework, then any operational theory has an ontological model. You could just kind of take a trivial one where lambda is just a complete description of the preparation, for example. Okay, so in order to actually get an interesting constraint out of this, we need to add something more, and that's where non-contextuality comes in. Sorry, I always forget about this bit. Before I talk about non-contextuality, we just need to think a bit about what happens if we have a preparation procedure that's implemented in a convex way. So it's a preparation procedure where the overall procedure P is that with probability Q, I do some preparation P1, and with probability 1 minus Q, I do this other preparation P2. So how is that preparation P going to be represented in the ontological model? Well, it better just be that with probability Q, I get the ontic state I would have got from P1, and with probability 1 minus Q, I get the ontic state I would have got from P2. Okay, so these really are supposed to just be probabilities, so they should be combined in exactly the way you would expect probabilities to be combined. Okay, so that's how we're going to represent mixtures. We're just going to represent mixtures at the operational level as mixtures at the ontological level. Good, so now I can get to non-contextuality. So non-contextuality relies on this idea of operational equivalence. So I'll talk about operational equivalence amongst measurements first. Operational equivalence says that you've got in principle, two different measurement procedures, M and M primed, but you notice that no matter how you prepare or transform the system, the probability distribution over the outcomes is always the same from both M and M primed. Okay, so operationally, if all you're looking at is the operational level, you have no way of telling whether you've implemented M or M primed. And remember, the principle of non-contextuality was that you shouldn't have differences at the ontological level that aren't represented at the operational level. So here we have the M and M primed. There's no difference between them at the operational level. And so by the principle of non-contextuality, there had better be no difference between them at the ontological level. Okay, which is going to mean that they give M and M primed give the same probabilities for outcomes for all ontic states. Okay. For our purposes, it's going to be useful to just think about that in a slightly different way, which is that we're going to think about this operational equivalence thing and just form the equivalence classes under this notion of operational equivalence. Okay, so I'm going to use the notation EK here to just represent all the different procedures that are operationally equivalent. So just some particular equivalence class of measurements. And then what we're saying is that the probability for the measurement outcome really only depends on which equivalence class of measurements you're in. And the reason I've used this notation EK is that in quantum theory, equivalence classes of measurements are exactly POVMs. Okay, if two measurements have the same POVM, then they give the same statistics. If they have different POVMs, then there's at least one preparation on which they give different statistics. And so for quantum theory, what measurement non-contextuality says is that the probability for a measurement outcome can only depend on the POVM element. And then we can do the whole thing again for preparations. We can talk about equivalent preparations. And then in quantum theory, again, those equivalent preparations are just represented by density operators. And the assumption of preparation non-contextuality is going to be that the probability for lambda given a preparation is really just a function of the density matrix. And that's how we saw it formulated in Matt Leafer's talk. And you then do the whole thing again for transformations, and you're going to require that the way you represent transformations only depends on the CP map and not on any other details of the transformation. Okay. So for the purposes of the results that I want to present, it's useful to draw diagrams. Luckily, we've already seen these in John Selby's talk. It's the advantage of being on the last day. So time went from bottom to top, and a diagram like this means that I have two systems. I apply F on the first one, G on the second one, and then after that, I apply H on the first one. Okay. And there'll also be two special types of operation. If I don't have an incoming system, then I just have some preparation of the system coming out. If I don't have an outgoing system, then I just have some measurement of the system coming in. And finally, we're going to have a convention that if we close a circuit completely, so we have no incoming or outgoing wires, then that just represents the probability of whatever we've drawn there. So in this case, this diagram is just equal to the probability of getting this measurement outcome, given that we've done this preparation and this transformation. Okay, so now to talk about non-contextuality, we need to make sure we've thought about operational equivalence. So in diagrams, we would say that E and E primed are equivalent if these two probabilities are equal for any preparation. And the way we're going to encode that in these diagrams is we're just going to bake it in. So we're just going to say that if two things are operationally equivalent, then they're just equal as diagrams. Okay. So in other words, when I draw something like this, I'm already talking about the operational equivalence class of measurement outcomes. Or if you're used to thinking of GPTs, then this thing represents an effect. Okay, so now I've done that, I can introduce another bit of diagrammatic notation that I don't think we've seen before, which is I want some way of showing these ontological models on these diagrams. And the way I'm going to do that is by drawing these purple boxes over things. Okay, so if I just drew P on its own, that would just represent the operational procedure of preparing P. But if I draw a box over it, that means what I'm asking for is the ontological model of that thing. So I'm asking for the probability distribution over lambda, given that I've done that preparation P. And now, because I said that two diagrams that are operationally equivalent are just equal as diagrams, that means that I've already baked in the assumption of preparation non-contextuality, okay? Because the thing I'm putting inside this box is just a diagram, so that's already an operational equivalence class. And so this probability for lambda can only depend on the operational features of P. It can't depend on the context. Okay, so this is just some way of representing the ontological model, and we're building in the assumption of non-contextuality. And we can do the same thing. We draw a box over an effect, and that gives us the probability for that effect in the ontological model, given the incoming context state. And finally, we can do the same thing for transformations, and that's going to tell us how the ontic state is transformed in the ontological model. And another feature of this notation is that we draw thick lines for the operational systems, and we draw these thin lines for the ontic states. So the boxes take you from thick lines to thin lines. And now this equation that I had before, that the ontological model reproduces the operational probabilities, we can just write that diagrammatically. I've already said that the operational probabilities are just written by closing a diagram. And now we just have the convention that if I join together two of these ontological boxes, then it just means that we integrate over the variable between them. Okay, so this thin wire here represents lambda, and then the fact that I've joined them up means we integrate over lambda, and this thin wire here represents lambda primed. Because that's joined up, we integrate over lambda primed. And so this whole thing on the right-hand side, we're just going to say is the diagrammatic form of this equation. Okay, so that means that this equality on the bottom is just a diagrammatic form of this equality on top. Okay, so now I can actually get to our structure theorem. So the idea is we're going to take this assumption of non-contextuality and we're going to derive a fairly strong constraint on what this ontological model has to look like. Okay. So our main assumption is something that we think should sort of just be part of the definition of non-contextuality, and it's something called diagram preservation. So what does diagram preservation say? It says that if we draw one of these boxes, these purple boxes over a diagram, we should be either allowed to draw it over the whole thing, or we should be able to draw it over each of the parts, and we should get the same answer. Okay, so here's an example of that. Well, and this is kind of a boring example because I've already said that this thing on the right here is just the calculation in the ontological model of this operational probability. Okay, so all I'm saying here is that the probability, when you calculate this probability using the ontological model, you calculate it in the usual way by considering the preparation, transformation, and measurement separately, and then summing over the ontic states. Okay, and so now, given that we have this assumption of diagram preservation, then the requirement that we reproduce the operational probabilities becomes this very simple equation here. Okay, so this instance of diagram preservation isn't really doing anything. It's just a different way of doing the standard notion of an ontological model. An assumption that's a bit more substantial is that over here I have the identity at the operational level. Okay, so this is the procedure that has no effect, transformation that has no effect at the operational level. And diagram preservation says that if I draw a box over that, then I just have the identity at the ontological level. Okay, so diagram preservation requires that if I have a transformation that does nothing at the operational level, it also does nothing to the ontic state. So that's possibly a bit more controversial. One way to think about why that's natural is that one way to implement the operational identity is just to wait no time at all. Okay, so you just do nothing for no time. Well, then it's fairly natural, since you haven't done anything and no time has elapsed, it's fairly natural to suppose that the ontic state is not going to change. And then in order to get from that to all the other different ways that you can implement the operational identity, for example, in quantum theory, by doing some unitary and then by doing its inverse. So you might worry that that's a bit more complicated. That could have some effect on the ontic state. But now we can just appeal to transformation and contextuality, which says that since that's operationally equivalent to that first thing of doing nothing for no time, then it has to be represented in the same way in the ontological model. Okay, so that's why we think that the operational identity should equal the ontological identity. And then another instance where we're going to apply diagram preservation is to consider an operational procedure here where we measure the system, and then based on the outcome of that measurement, we re-prepare the system. Okay, so this is kind of like a measure and prepare channel or a entanglement breaking channel. So that's the description at the operational level. We've measured the system and then we've re-prepared it. But diagram preservation says that the way we represent that overall transformation has to be the same as the way we would represent that measurement on its own, multiplied by the way we would represent that preparation on its own. Okay, so, or in other words, since at the operational level, there's no influence between the incoming system and the outgoing system, except that possibly that this preparation can depend on this measurement, that has to be reflected at the ontological level. So the only connection between the outgoing ontic state and the incoming ontic state is whatever connection there is between this preparation and this measurement. So in equations, we're saying that the representation of the operational identity is some kind of direct delta function on the ontic state. And we're saying that the representation of this measure and prepare channel is just obtained by multiplying the representation of the measurement with the representation of the preparation. Okay. So that's diagram preservation. The other assumption we need is not an assumption about the ontological model, it's just an assumption about the operational theory. And it's one that has been considered a lot in the GPT literature, called local tomography, which basically just says that if you want to determine whether two things are operationally equivalent, it's enough to just check it on product states and product effects. Okay, so if the procedures T and T primed give the same probabilities on product states and product effects, then they are indeed the same transformation. Okay, so this is satisfied in quantum theory, it's satisfied in classical probability theory, but for example, it's not satisfied in real quantum theory. Okay, but so we're going to assume this local tomography. And in fact, for our purposes, it's useful to have an equivalent formulation, which is that any transformation can be decomposed as some linear combination of these measure and prepare transformations. So it's important that these coefficients in this linear decomposition don't have to be positive, so they're not necessarily probabilities. So I'm not saying that every transformation is a mixture of measure and prepare channels. I'm just saying every transformation can be written as some linear combination of them. So it might not be totally intuitive that this is equivalent to the more kind of natural version of local tomography you saw in the previous slide. But yeah, you probably just have to take my word for it. It might help to think about the case of quantum theory, where in quantum theory we have the Choi-Jamalkowski isomorphism that says that if we're talking about some transformation, we can equivalently think of it as being like a bipartite state. And so if you formulated this equation in the kind of bipartite state language, it would just be saying that any state, even an entangled state, can be written as a linear combination of product states. Okay, because the Choi-Jamalkowski isomorphism represents these kind of transformations as product states. And that kind of version, it's easier to see that that's basically another way of talking about local tomography. Okay, but we can prove this in general, that this is equivalent to local tomography in any GPT without using the Choi-Jamal-Kapsky isomorphism. Okay. So those are our assumptions. So I can finally get to the statement of the theorem. The theorem says that any of these diagram preserving non-contextual models of a locally tomographic theory can be written in a special way. Okay, so the way that we represent some transformation in that ontological model is that we just surround the transformation with this gadget chi and its inverse. Okay, so that's a little bit confusing. What is this chi business? Well, it's useful to just consider the special case where the transformation is a preparation. So in that case, we don't have an incoming system, so we can forget about this bottom bit, and we just have chi. So basically, what chi is it's just a different way of writing the way that we go from preparations to the distribution over ontic states associated with that preparation. Okay, so in other words, this function chi is just an encoding of how we represent preparations in the ontological model. And then what the structure theorem is saying is that once you know how you represent transformation, how you represent preparations, sorry, using this chi, then you know automatically how you represent any other transformation. So, and that includes measurements. So it's saying that the only freedom when you're constructing a non-contextual model is you decide how you want to represent preparations, and then you get the representation of transformations and measurements for free. Whereas in the definition, it kind of looks like you could specify all of those things separately. Okay, so I'm a little bit behind time, so I'm going to try and go through the proof quite quickly. So the first step is we just use that equivalent formulation of local tomography. And now we sort of remember right at the start, I said that convexity at the operational level is reflected by convexity at the ontological level. And you can do some kind of standard mathematical tricks to extend that from being convexity to just being linearity. So basically, we can assume that these purple boxes are linear and pull these coefficients outside. Then we can use diagram preservation to split this up into the representation of the measurement and the preparation. Step 2 is to focus on how preparations are represented. And the idea here is, again, just to think about convexity, extend that to linearity, and therefore we can just kind of adopt the idea that the way we're gonna represent a preparation like this is by just drawing this box chi after it. So we're just defining chi to be equal to this thing on the left-hand side, and it's kind of valid to draw it like this because it's a linear thing. Okay, so we're not saying that this chi is actually some physical transformation that you could operationally achieve, but it mathematically is a linear transformation, and so we can at least include it in our diagrams in this way. And now we need to think about the representation of effects, and we can just do the same thing and argue that this is also linear, and so there's going to be, we can represent that using some gadget phi. Okay, so combining those two steps, we have that the representation of the transformation can be decomposed into the representation of the preparations and measurements that we're doing using these chi and phi things. And then we can just use linearity again to put that back to being the transformation in the middle. So now we're almost at what we want here. The only thing we need is that this phi is actually the inverse of this chi. So that's the final step. The way we do that is we consider the case where this transformation is the identity. So now we just have the identity between chi and phi. By diagram preservation, that's equal to the ontological identity. And now we also consider a very simple prepare and measure experiment, represent that in our ontological model, use diagram preservation again. and then just use the definition of phi and chi. And now, so what we have is that chi followed by phi gives us the same probabilities as the identity at the operational level for all preparations and all measurements. And so by local tomography, this transformation is just equal to the identity transformation. Okay, so now we have that phi followed by chi is the identity, and we have that chi followed by phi is the identity, which means that phi is the inverse of chi, which is exactly what we wanted. Okay, so that's our structure theorem. And I should just point out, so I said that one thing it's giving us is that once you've fixed the representation of preparations, you fix the representation of everything else. The other useful thing it gives us is that that representation of preparations is invertible. Okay, so this chi has this inverse, chi inverse. And one consequence of that is that the dimension of the thing coming into chi has to equal the dimension of the thing coming out to chi for it to be invertible. And the thing that's coming in is like the operational state space. And the thing that's coming out is a probability distribution over ontic states. And so what this means is that the number of ontic states in your ontological model has to equal the dimension of the operational state space, which is quite a strong constraint on the model. Okay, so I think that's about all I wanted to say about the structure theorem. So in my remaining time, I'll talk a little bit about the stabilizer subtheory. So what is this subtheory? It's something that comes up quite a lot in quantum computation, especially for quantum error correction. So we want, if you've come across it at all, you're most likely to have seen it in the case of qubits, but we want to talk about it in arbitrary dimension. So we need to define this omega as being a d-root of unity, and then we define kind of generalizations of the Pauli X and Pauli Z operators to arbitrary dimension. So the generalization of X just increments you in the computational basis, and the generalization of Z just gives you a d-root of unity in the computational basis. And then we define these things called Weil operators that are just given by a power of Z times a power of X. Okay, so this is like a generalization of the Pauli operators for qubits. And then the stabilizer subtheory is just defined by the states that are specified as eigenstates of these Weil operators. Transformations are unitaries that map Weil operators to other Weil operators. And the measurements are basically just measurements of these Weil operators. Okay, so that very briefly is the theory we're talking about. For our purposes, the only transformations we're going to care about are the Weil operators themselves. So these are unitaries, and they're allowed in the stabilizer subtheory because they do map Weil operators to Weil operators, and the kind of generalization of the Hadamard that's given here. Okay, so those two things together don't quite generate the entire Clifford group, but they're enough for our purposes. Okay, so what's our result? So we look for a non-contextual model of this stabilizer subtheory, and in odd dimensions, we find that there's a unique non-contextual model. And in even dimensions, we find that there's no non-contextual model at all. Okay, so in other words, the even dimensional stabilizer subtheory is contextual. So this is something that was definitely already known for D equals 2. And probably people expected it to also be true in all even dimensions, but we couldn't quite find a proof of that. But the most important result, I think, is this one in odd dimensions, that there is only one non-contextual model of the odd dimensional stabilizer subtheory. Okay, so I definitely don't have time to prove this result, but I do just want to kind of give you a quick sketch of it. The reason I've put these both in the same talk is that the first step of the proof is just to apply the structure theorem that I talked about in the first part. Okay, so this stabilizer subtheory is a locally tomographic theory, so we can apply the structure theorem. And in particular, we get that consequence about the number of ontic states being equal to the dimension of the state space. And this is just quantum theory, so the dimension of the state space is d squared, right? The number of parameters in a d by d density matrix is d squared, number of real parameters. So that means that we know immediately using the structure theorem that our ontological model has to use d squared ontic states. Okay, so then the next step is just to apply a standard argument in non-contextuality, which you can find in Rob Specken's original paper about this notion of non-contextuality, which says that any non-contextual model of quantum theory has to represent projective measurements deterministically. Okay, so if I have a projective measurement, then the probabilities for the outcome given the ontic state are either 0 or 1. Okay, so that's just a standard argument in non-contextuality, and that applies just as well to the stabilizer formalism. So now if we consider two particular projective measurements, measurements of x dagger and measurements of z, then in the ontological model, each ontic state just gives us some fixed outcome for each of those measurements. And so what we're going to do is we're going to label the ontic states by the outcome P for this first measurement and the outcome Q for this second measurement. So far, I've only kind of given you a way to associate, like given a lambda, I've given you a way of associating a P and Q with it. You just see which deterministic outcome it gives you for these two measurements. But what we can also argue is that for every PQ, there must be an ontic state that gives you that. And that's basically because of the kind of unbiased nature of, mutually unbiased nature of these two measurements. If you're in an eigenstate of one of them, then you have a uniform distribution over the other one. And that basically means that you need all possible combinations of P and Q in your ontological model in order to reproduce that. And since we already know that there are only d squared ontic states, and we have d different outcomes for this measurement, d different outcomes for this measurement, in other words, d squared different combinations PQ, then in fact, this labeling is a bijection. Okay, so in other words, we can associate every lambda with a PQ. We know that we need to use all of the PQs, and we know that there are d squared lambdas. And so that means that the ontic states are just these pairs of PQ. Okay, so now we've gone from having this very general kind of ontic state floating around to just knowing that the ontic state is specified by the outcome of these two measurements. Okay, so that's a drastic simplification, and most of the work is being done by the structure theorem. And then we just kind of get into the weeds of the stabilizer theory a bit. We look at how those Weil operators, when considered as transformations, we look at how those affect the outcomes of these two measurements, and we conclude that the effect on the ontic state has to be kind of the thing you would expect. And we do the same thing for the Hadamard, work out how that's represented in the ontological model. And then once we've done all that, we find that the only thing that's left is to decide how the other measurements of the other Weil operators are represented on the 0, 0 ontic state. We get some kind of constraints on those. This one comes from requiring that the probabilities are real. This one comes from the way that the Hadamard is represented. And we can combine those to get this nice thing here. And then the important thing is that in odd dimensions, there's an inverse of 2 mod d. So we can just solve this equation to find out these values v, p, q that we need to define the model. Whereas in even dimension, it turns out that there are just no solutions. So that's why there's no model in even dimensions. And so what is this model that we get in odd dimensions? Well, it's exactly something that's been talked about a lot before. It's Gross's discrete Wigner function. So I'm out of time, so I'm not really going to say much about this, but basically this thing that we found in our theorem shows up in the definition of Gross's discrete Wigner function. So it all fits together that the unique non-contextual model of the stabilizer subtheory in odd dimensions is exactly this Gross's discrete Wigner function that's already been talked about in the literature. Okay, so with that, I'll just put up my conclusions and hopefully we have a bit of time for questions.
Okay, thank you, Matt. So we have time for 2 questions, 2 or 3 questions maybe. Somebody in the audience? Is there an online question? No? So let me begin with a question just to understand a bit better the diagram preservation that you're putting up here. So it all makes sense to me. I still think I have to wrap my head a bit around it a bit more. I suppose that if you have different wires and you're talking about the ontological level, you're also putting some conditions about the wire structure being preserved also by the hidden variables. So I'm thinking a bit about comparing your circuits, for example, to the idea of these quantum networks, say a Bell scenario. We say I have this experimental causal structure, and then I demand that this causal structure is also represented at the ontological level. So are these circuits that you're now drawing and demanding non-contextuality, is this a kind of generalization of this demand of preservation of causal structures? I'm just trying to understand a bit better this relation, perhaps.
Yeah, I think that's definitely a good way to think about it, is that it's about preservation of causal structure. So like in this particular example, like you can think of it as that what we're saying is that at the operational level, there's no causal connection between the incoming system and the outgoing system, other than the connection between the preparation and measurement. And we're requiring that lack of causal connection at the operational level is reflected as a lack of causal connection at the ontological level. And indeed, if you applied this diagram preservation assumption to the standard operational description of a Bell experiment, then it would imply local causality, basically. So from that point of view, it's actually quite a strong assumption, like it kind of encodes the usual notion of locality. Yeah, there's kind of a whole rabbit hole you can go down about whether it's good to build in such a strong notion of locality. But the kind of nice thing about our result is that we don't actually need diagram preservation in full generality. We only need these particular instances that I've shown here. And so if you're not happy with imposing it in general, you might at least be happy with imposing it in the cases where we need it. But the way you were talking about it is a good way of thinking about the general assumption.
Yeah, it's surely a set of very intuitive assumptions. Thanks. Now we have online questions. Pardon? Okay, Costantino.
So it's not related to online. So we have also a couple of online questions. Maybe I will, yes, I will allow them to talk. Yes, So thanks, Matt, for the talk. I had a question about this discrete Wigner function. So this last part of your talk. So I think you said at the beginning that you're looking at this stabilizer subtheory. So in this case, you will have the let's say positive Wigner function. So will be the so what happens in the other case? Maybe if you have some state that doesn't have a positive Wigner function, can you still have some sort of non-contextual model in this, let's say, in this framework of contextuality? Or I don't know, have you explored this this direction, or what can you comment about that?
Right. So firstly, one thing I maybe didn't emphasize enough is that the notion of an ontological model includes the requirement that the probabilities are positive. Okay, so that's absolutely essential for everything that we've done. Like if you allowed negative probabilities, then there would be a whole bunch of models of the stabilizer formulas, and it's important that we're requiring the probabilities to be positive. Okay, so now what happens if you think about some state, say, that has a negative Wigner function? Well, then you can consider the operational theory that is the entire stabilizer formalism plus this extra state that has a negative Wigner function. Okay, what does our result say about that? Well, it says that that's contextual. And the reason is that just the stabilizer bit on its own, we know has to be represented using the Wigner function, which would mean that when we add this extra thing, that still has to be represented by the Wigner function. But then the Wigner function represents the extra thing negatively, which isn't allowed. And so therefore, there is no non-contextual model of the stabilizer formalism plus that extra thing. And so that gives us a kind of parallel to what was shown in this paper by Howard et al. Using the traditional Cauchy-Specker definition of non-contextuality, where they showed that basically the stabilizer formalism plus any negatively represented state gives you contextuality. So we kind of get that for this general notion of contextuality.
Okay, thanks. Thank you very much.
Okay, we should go to one more online question.
So we should have Gemma again, I think.
Yes, Gemma, speak up.
Hi, thanks a lot for your talk.
Sorry, I promoted.
I was trying to understand your second slide, and I don't think I do. So I took it to mean something like the only things that exist are those that make an operational difference or something like that. Something like that. Yeah. But then I was trying to see in your next slide, you seem to have like a something that depended on a for all P and T, which is generally an infinite set. This one, exactly. As far as I see, that's an infinite set. And that makes me very uneasy, and I wonder if having an infinite set is here something operational. Well, I would claim it is not operational, but can you please clarify? Or I'm sorry that I'm unclear about that. Can you please explain whether that?
Yeah, so it's definitely something to be nervous about, is that we have this quantifier over all possible preparations and transformations here. So you might ask if this operational equivalence is really an operationally meaningful notion. In the case of at least finite dimensional quantum theory, there's kind of a fortunate fact. I mean, basically what makes it finite dimensional in the GPT sense is that there's a finite number of preparations and transformations that you need to check. Okay, so there are these finite sets of tomographically complete preparations. And in fact, if you just check that this is equal on that finite set, it implies it's equal on all the other ones. So if you have a finite dimensional operational theory, then in fact this quantifier that looks like it's over an infinite set, you actually only need to check a finite set.
Okay, but
you might.
Are you assuming the dimension of the physical system for that?
Yeah. So I mean, this is a whole, like, if you really want to check this in an experiment, in order to do some kind of experimental test of contextuality, then that's definitely something that you have to worry about. Is do you really understand what the dimension of the system is? As theorists, when we're looking at something like the stabilizer formalism, we just know what the dimension is. But yeah, if you're trying to demonstrate everything in an experiment, you definitely have to worry about that.
Thanks.
Okay, I think we wrap up here. Let's thank Matt again.